Let's take a look at this problem. So we're told we have a car which is bouncing up and down on its springs. Okay, so this is a mass on a spring problem. And I'm going to think about it this way. I'm going to take the whole car as a single mass, bouncing up and down on a single spring. Okay, and in fact, we know that the car has 4 springs, 1 on each wheel, but we can treat it this way. This is a model, and it's going to work just fine. So I have the mass of the car, and I have it on a single spring. So I have a mass m on a spring constant, k, and we know this. The frequency for a mass on a spring is just 1 over 2 pi times the square root of k over m. Now we're told this. When the car is empty, it's got a mass of 1,200 kilograms. It bounces up and down on its springs when it's empty 2.0 times per second. So what that's telling me is this. The car bounces at a frequency of 2.0 hertz when it's empty. That's equal to 1 over 2 pi times the square root of k over m. In this expression, I know the mass of the car. Okay, I know the mass. That's 1,200 kilograms. I know the frequency, that's 2.0 hertz. What I don't know is the spring constant k. So I can use this information about the car to calculate the spring constant. Once I know the spring constant, I can figure out the frequency when I've added additional mass to the system. But the first step is going to be this, to take the default case that we're given of the empty car and use that to find the spring constant. Now to aid in this, what we're going to do is this. I'm going to take this relationship, f is equal to 1 over 2 pi times the square root of k over m, and I'm going to rearrange it so I can solve for the spring constant in terms of the frequency. So I'll square both sides of the equation. F squared is 1 over 2 pi all squared times k over m, so the square root disappears. Then I rewrite it this way. The spring constant is equal to 2 pi times the frequency all squared times the mass. Okay, so this is my relationship. It's the same as this one, but I can use it to solve for the spring constant. And with this all in place, I'm ready. And my first step of the solution is going to be this. First off, I'm going to figure out what is the spring constant for the car when it's, by using the data from when it's empty. And for that, it's just this. It's 2 pi times f squared times m. Well, I'm looking for the situation when the car is empty. And when it's empty, the frequency is 2.0 hertz. The mass is 1,200 kilograms. And so I solve for a spring constant. If I do that, what I get is this. I get 1.895 times 10 to the 5th newtons per meter. Now I'm keeping extra significant figures because this is the intermediate stage of the calculation. But let's do an assessment of this number. This number right here is big. That is a very stiff spring. That's saying if I compress the spring by 0.01 meters or 1 centimeter, I end up with a force of about 2,000 newtons, which is a force of about 400 pounds. So what you're saying is push your car down by a centimeter, it pushes back by 400 pounds. That makes sense. That makes sense. You want the springs on your car to be pretty stiff, okay? So that number seems reasonable. Okay, now what we do is this. We say now the situation's changed. I have a mass bouncing up and down in the springs, except things have changed. I've taken the 1,200 kilogram car, and to it, I've added 4 70 kilogram passengers. And so the total mass in motion is the sum of those two, 1,480 kilograms. Okay, so it's just 4 times 70 plus the 1,200. The spring constant of the spring is exactly what we've seen before. It's 1.895 times 10 to the 5th newtons per meter. And so I can calculate the frequency that I would expect. Well, the frequency is 1 over 2 pi times the square root of k over m. I know k, I know m, and I can just solve for the frequency. And if I do that and I round it to 2 significant figures, because this is clearly a 2 significant figure problem, I get 1.8 hertz. Now let's see if this makes sense. We start out with a mass of 1,200 kilograms. We finish with a mass of 1,480 kilograms. The frequency of the car bouncing up and down on its springs is 1/2 pi times the square root of k over m. If I increase the mass, I'm going to decrease the frequency. So if this number goes up, I expect the frequency to decrease. Except this number is in a square root. So a small change in mass is going to make an even smaller change in the frequency. The mass has gone up from 1,200 to 1,480. So it's gone up by, a little bit more than, I would say by about 20% or so. And so I expect to have a fairly small change in the frequency. And in fact, it drops from 2 hertz to 1.8 hertz. It's dropped by about 10%. 20% change in mass, 10% change in the frequency. Frequency decreases, but not by very much. And so our final stage in the problem, we can say this. Our assessment is the problem matches the way we know the world works, which is a great final step in any problem.